Hello, Vaibhav.
Yes, sir.
Am I audible?
Hi, yes, sir.
Hello.
Hello, good morning, Snehal.
Good morning, sir. Welcome all the participants and delegates in this 1 week online training course on crop weather modeling, tools for climate smart agriculture.
आदिनाथला घेऊन जा. मी हे सेशन चालू करून देतो.
Now I would like to request our organizing secretary, Dr. R.P. Andhale, sir, to introduce
Hello,
our
good morning.
today's speaker. Good morning,
Yes,
sir.
sir.
No response from this.
Yes, sir. Patel sir, बोलिए sir. Hello. Patel sir, did you want to say something?
Hello.
You want to say something, sir? You are audible, sir. We are able to hear you. Vaibhav.
Yes, sir.
Please see what is the problem. I think Patel sir is not able to get the sound.
Okay, sir. Let me check, sir.
Patel sir, this is Dr. Ravi Andale. Are you able to hear my voice? Hello. Hello.
Hello, good morning.
Yeah, welcome, sir. Welcome. This is Dr. Andale, organizing secretary. Now I think it is set. Everything is. Vaibhav, can we start now?
Yes, sir. You can start, sir.
Okay. Good morning, all of you. And I'm happy to welcome you to this day 2, session 1. And we are having with us today's speaker, an eminent scientist from ISRO, Dr. N.R. Patel, who has completed his education from Gujarat Agriculture University. He has specialization in geo and earth observation, terrestrial biogeochemical cycles. He has very prestigious and track record. Like he is the recipient of the awards like Hariom Ashram Prerit, Dr. Vikram Sarabhai Research Award for Space Application. He is the fellow of Bhuvigyan Vikas Foundation, New Delhi, and expert member on various selection committees of the various universities. Member
Hello?
Executive Council of our association of. Yes, sir. Please. Hello. Are you able to hear, sir?
Yeah. Now I can. Okay.
Yeah.
Yeah.
Dr. Patel is also the member of Executive Council of the Association of Agrometallurgists,
Yeah.
and the reviewer of various universities for PhD thesis, and referee for various journals, and very impressive background. We are having a renowned, we are having a very renowned scientist with us today in the field of remote sensing. So I welcome you, sir, and I will hand over the floor to you. Thank you very much. Thank you, sir.
Let me see. I have not done. Where it is gone? I have to share this slide. Nah.
Yes, sir.
Yeah.
Sure.
That okay, I'm trying because my people are not here.
Okay, no problem.
I'll see.
Vaibhav, can you
No,
guide?
I'll just ask my people.
Agronomy department आहे आपलं.
ये हर दिन अलग अलग प्लेटफॉर्म भी है ना.
जूम है.
हाँ, एक दिन जूम चलता है, दूसरे दिन दूसरा चलता है.
ये चालू ही था. इधर इसके पास.
Sir, is it visible right now?
Yes, sir. Yes, sir.
Okay.
You can put it on slide share mode, slideshow mode.
Slideshow mode. Justin, 1 minute. उसको स्लाइड शो करके you can keep this, okay? ये सारा बैकग्राउंड निकालो. ये स्लाइड शो में रखते.
Yes, sir.
Good morning, dear participant. It is my pleasure to interact with the student, faculty, and scientists from agriculture discipline, and particularly agrometeorology, physiology, or agronomic background. Yes, I am basically agrometeorologist, agronomist, and agrometeorologist, and translated my expertise into a remote sensing and its application for the agronomy and agriculture meteorology. So today topic what I have been given is one of the most touching to my discipline and also to my heart. Geospatial crop modeling for climatic risk and climate change impact assessment. Particularly crop modeling. When we talk about crop modeling, they are simply the mathematical representation of the physiological principle built governing the various processes of the crop. Crop modeling has been variously utilized for crop management, climate change strategy, developing adaptation strategy for climate change impact assessment, agroclimatic risk assessment, and many other areas, whether pest, disease, nutrient, so many areas it has been widely used. But today we'll talk a little bit different. Crop modeling is there, okay, being practiced across the world by agriculture community mainly agronomists and agrometeorologists at experimental level. But today we'll discuss how we can extend our knowledge of agrometeorology or crop modeling to a large area or regional scale, continental scale, or national scale. Then huge benefit can be achieved. If it is point-based or experimental farm level, may not be accurate for the field condition. So here I have divided my lecture into a different outline or categories. First factor which controls the yield and yield gap, because whatever yield farmer receive at his field is quite different from what is being modeled by our agriculture scientist or agriculture researcher at the experimental farm level. Because experimental farm level is an optimal environmental condition or optimal management condition. It usually differs what received at the farm scale. Here, so our interest is to model crop yield over large area and at the same time at the farmer's field, not at the experimental farm. So we need to discuss yield gap also. Then geospatial technology. Geospatial technology, that is nowadays a buzzword among the students, scientists, or faculties across various disciplines. Everybody want to make use of digital age, and geospatial technology is a part of that information technology and the digital age. It can revolutionize the way we think about how agriculture grows, what are the agriculture decisions being taken up by the government authorities. All depends on the how best geographical information we can provide for that. Third, crop modeling with the remote sensing. So all this is very basic that okay, most of the agrometeorologists knows. They study in their PG studies mainly the Montes model, light use efficiency approach. That will discuss how that can be used along with the remote sensing for crop yield prediction. Fourth, climate crop modeling, because these days there is a lot of progress being made to improve weather forecast, and such weather forecast can be assimilated into a crop model and for the better early crop forecasting. Then we'll discuss specifically for all Maharashtra or Marathwada Agricultural University specific example of cotton crop modeling for Maharashtra region. Then we'll discuss geospatial crop modeling also and climate change impact, geospatial modeling for agroclimatic risk, and crop monitoring and early warning for the large national or international scenario. So first, let us understand what is yield, potential yield, what are the attainable yield, and what is actual yield. Potential yield, that is mainly determined by the genotypic potential or genetic potential. So most of the variety, whether it is in Maharashtra or Punjab or Haryana, variety genotypic potential, it has got almost 5 times. But what realized on the farmer ground or farmer field is quite very low, because genotypic potential decided by the radiation, photosynthetic properties, and other elements. But to which extent it can be attained with some management, improved management like water management, nutrient management is called attainable yield. So if water and nutrient is adequately supplied, then whatever yield you will get is attainable yield, and it may or may not be equal to the potential yield. Then third is a actual yield. That is what farmers get. So to certain extent you can manage through water availability, water supply and nutrient. You can manage and get better yield. But there are reducing factors also, like pest and disease, pollutants. All these are beyond our as on today manageable to certain things. So farmers get even yield is reduced by this factor. So farmer gets almost, you can see that almost less hardly 6 to 7% of the potential yield, that is a 20,000 kg, and farmers get only 1,500 kg per hectare. That is the yield gap. If you see this yield gap between potential attainable and the actual yield. So by having management, you can improve to the attainable yield, but you can get attainable yield, but actual what farmer is getting, that is still there is a gap. So you see here, there is one international studies where in most of the central India, we are seeing mainly attainable yield is very low compared to the Indo-Gangetic Plain and Peninsular India. Indo-Gangetic Plain, mainly the rice wheat system, good varietal genotypes are there, high level of irrigation and nutrient management, input managements are there. So the farmers are practicing high level of management and try to get highest percentage of the attainable yield. But central India, some part which is highly subject to the scarcity of water or some kind of dry land agriculture is practiced, those area still we need to have improvement in the attainable yield. So little bit I'll brief you about what are these geospatial technologies. Government of India, particularly ISRO, Indian Space Research Organization, has been involved in developing space technology for with respect to the satellite sensor, launch vehicle, satellite transportation, communication technology, and as of now, we are venturing into a GPS, means global navigation technology. So satellite based space technology that provide application in the form of remote sensing, GPS, geographical information technology, then this communication technology. All these are very much useful for the informed decision making. So Earth observation, particularly we can say remote sensing data, which has got unique characteristic, like those data has got multispectral observation, different kind of partial resolution, like we have Cartosat data which is available at 1 meter resolution, to today we have got OCM and INSET which is 4 kilometer resolution. OCM is 300 meter resolution NDVI data set we are getting. So there are various from 1 meter to 1 kilometer satellite data with the partial detail you can get today from the space sector. At the same time, temporal resolution is varying. There are satellites which provide almost in a day twice image. And there are geostationary satellite like INSET or Meteosat. INSET from India and Meteosat. INSET 3D, what I am talking. There, you can get even the half-hourly image of the water vapor, precipitation, radiation. All you can get half-hourly database. So all these information are very much vital for agriculture crop system modeling and finally assessing the climatic risk assessment. GIS is nothing but it is a information system that enables you to input, store, display, analyze, and visualize the partial and non-partial data. So once you are having the data, remote sensing data, which are available in the both partial format and non-partial format also, they can be integrated with the GIS. So GIS database may be not only the satellite imagery, there are airborne imagery, there are UAV, unmanned aerial vehicle or drone related acquire image. And there are also in situ measurement network, AWS observation or automatic weather station data. And there are also inventory, ground station, LAI, ground observation of LAI, leap area index, also you can say resistance or you can say evapotranspiration, all ground observation can also be integrated with the GIS. So all this play a very role to integrate within the GIS and provide critical information for the various agriculture related decisions. Then there is a GNSS, Global Navigation System, which provide location about the locational information about the earth feature or the object. Suppose if we link it with the precision farming, then this GNSS that can help you to detect the location of your equipment, which supply which spray pesticides or apply fertilizers. So for precision farming, GPS is very critical. So we require very high resolution or very high accurate GPS, which can help you to do precision farming. So all these technology are working in a synergistic manner: GPS, remote sensing, and geographical information system. So these all, if you learn and integrate with any discipline of agriculture, it has revolutionized the way you analyze data and develop a application for the user friendly application, what I mean to say. So first of some background, I can say what potential exists with respect to the space application in agriculture. So space observation have been utilized since long time, more than 30 years, and particularly India, lot more any application. Particularly if you see the agriculture sector is the major user of the Earth observation data or satellite data. Today, more than 75% of all satellite data being used by the agriculture community, with ranging from agriculture land mapping, crop area estimation, yield estimation, drought assessment, horticulture crop assessment, crop insurance studies, climate change assessment, then also pest disease, soil mapping, fisheries development, or any sector you name. Today, nowadays, okay, even veterinary disease informatics, whether it is animal husbandry, fisheries, poultry, agriculture, soil, water conservation, watershed prioritization, rural panchayati raj or rural development, every sector. Now it is vitally being used to make informed decision or directly create natural resource database for the various applications. But India as backbone of agriculture economy. So, and this satellite technology has been regularly used for the update of the crop production statistic and providing vital input for the sustainable agriculture. So what is our goal here today is a crop yield modeling for the crop forecasting and the climate change risk assessment. So remote sensing or particularly satellite data plays a key role in providing important input information about the crop production statistic to achieve sustainability of the agriculture. Satellite today available are in the optical and radar domain. They work for the monitoring agriculture. Earth observation facilitate not only the spatial distribution of crop, they enables us to monitor growth, to monitor abiotic and biotic stress, and also we can assess early loss of the early crop departure or crop loss. So first try to understand here how satellite remote sensing works. Particularly it is working based on the interaction of the electromagnetic radiation with the object. Here our object is the vegetation. Vegetation has got green leaves, and this green leaves has got chlorophyll, which is a pigment. Chlorophyll pigment is vital for the photosynthetic activity. So how plant makes food? Plant makes food in the presence of carbon dioxide and water. When chlorophyll absorbs the sunlight, and that light energy is converted into a chemical energy. So CO2 and H2O combine and makes carbohydrate in the presence of catalyst. So because of this photosynthetic light which is absorbed by the leaves, its reflectance is very less in the visible range. That is, you can see 0.4 to 0.7 microns. That is a visible wavelength and very much useful for the photosynthetic activity. Beyond 0.7 micron, you can see there is a steep rise in the reflectance. That is, which is the NIR, near infrared range. So in near infrared range, there is a cell wall air interface. At the cell wall interface, there is multiple scattering take place, Because of multiple scattering, reflectors in NIR is very high. So if healthy crop is there, NIR reflectors will be very high. If the stress crop is there, NIR reflectors will be less. Then there are 3 bands. Beyond that, 3 short wave infrared water absorption band, which is located at 1.4, 1.9 and 2.4 micron. So these are the water absorption band, because so they absorb short wave infrared wavelength due to presence of water in the plant leaves. So plant water thickness, it is called liquid water thickness. So when our plant is irrigated, it has got high water potential. So high water potential, so it absorbs short wave infrared wavelength. That is why this short wave infrared wavelength is ideally suited for monitoring agriculture drought also. Apart from the visible and NIR, you can generate NDVI. But here this is also useful for generating some land surface wetness index, which are vital for assessing water stress in the crop canopies. So here you see how you can generate normalized different vegetation index as a proxy of crop vigor or as a proxy of biomass or photosynthetic activity. Now here see normalized vegetation index. That means on the left side you are seeing there is a green plant. On left side, right side there is a stress plant, that yellow. So green plant is there, which has got higher near infrared reflectors around 50%. For visible reflectors is hardly 8%, because most of the light is being absorbed by the chlorophyll, so very less reflectors. But you see in the stress plant, 40% is near infrared reflectors and 30% is a visible. That means more reflectors is there in the visible due to less absorption of the by chlorophyll, because chlorophyll content is very less. So when you make in the NDVI, then NDVI near infrared minus red divided by near infrared plus red. So final that index gives you a 0.72 for healthy crop, and for this stress crop it is giving a NDVI value of 0.14. So NDVI is a very good measure of the stress crop, healthy crop, biomass, crop vigor, leaf area index, all are highly related. That is why remote sensing derive these satellite measures. They are vital indicator of the crop health, crop status, actual status of the crop. So they can be integrated with the weather data and useful for the crop modeling. So which are the other all this information possibly retrieved from the remote sensing data? There are different kind of sensor, satellite sensor available, like biophysical variable, leaf area index. Leaf area index, it is a ratio of horizontal leaf area to the ground area. Then fraction of absorbed photosynthetically active radiation, vegetation cover, and crop phenology. Crop phenology, a timing of occurrence of crop growth stage in response to abiotic factor. So these all biophysical variable possibly retrieved from the all optical satellite data, whether they are MODIs, LIS3, advanced SIFs, or SPOT. Similarly, hydrological variable, any sensor which has got either microwave or thermal satellite data are very much useful for rainfall. And then also evapotranspiration like AOHR, MODIs, Landsat, they are very widely suited for the evapotranspiration. Then soil moisture, there are satellite like that, microwave satellite, reset, mainly the L band, that ASMOS, NISAR, all are useful. So this, and then currently nowadays at coarse resolution, new kind of methodology like magnitude, gravity, change in the gravity magnitude is possible with the GRACE data. You can use GRACE data for gravity field, and change in the gravity can help you to detect change in the total water storage content. So particular hydrological cycle understanding and runoff and other water balance component you can easily get from the GRACE data also. So we have got now the TRM also, which provide high resolution rainfall at the resolution of maybe 1 kilometer or 4 kilometer resolution, and a very vertical resolution is also there. Now we'll come to the crop model, because this is all what I will talk, that is all basic. What are the remote sensing data characteristics? But we can see here how different crop model, statistical and empirical model, mostly all across globe, they are the most robust and operational bearing, relating weather variable with the yield. It has been practiced by the agrometeorologists across India to develop statistical crop weather analysis model. But if weather data is available at the right time and right location, because problem with this kind of model is that we don't have number of observatories, we don't have that partially explicit weather information available, because today we are having hardly 600 observatory A class. So maybe one observatory for one district. So one district level, you can get one model for the one district. But nowadays within a district, weather is highly variable. Rainfall is varying, temperature is varying within district. If there is a heterogeneity with respect to the land use, terrain and soil types. So because India is a kind of country where we have got high degree of heterogeneity in landscape, mainly terrain condition, land use and soil, which cause large variability in the weather. So we cannot capture good weather for representative weather with the one observatory. So this kind of data may be useful for the district level modeling, but within district, block level or village level crop yield estimation for the precision farming or crop insurance kind of activities, we need to have a high resolution crop forecast and crop risk assessment. Whether if we are talking with the disaster like flood risk or flood damage or drought damage, we need to have a village level crop yield loss estimation for crop insurance. So then we need to have model with a high resolution weather, which is not possible. So we need to use some kind of data which or some kind of technique which are highly acceptable or which are amenable with the satellite observation. So that is a semi-empirical model or semi-empirical physically based growth model, which is called efficiency based model or light use efficiency based model. So this is model previously given by Montet. It require not straightforward physics is there. It is a deterministic kind of model, and it require phenological scale. It is based on the relationship of the amount of absorbed photosynthetically active radiation and its conversion into a dry matter. It is suited for the irrigated agriculture. If there is a stress is there, it cannot take care of the stress condition. Then there are process-based simulation model. Process-based model, crop models are nothing but realistic representation of crop physiological and process and principle governing the crop growth and development. So these are process kind of model where inbuilt program that simulate behavior of plant as a function of weather, soil and the management condition. They are the continuous daily time step model and simulate dry matter, phenology, water balance, and finally yield. So but this kind of model require genotypic and phenotypic coefficient. They require crop state parameter. They also require daily weather data, soil condition, and management input also. So data requirement is very high. So that is a problem with the simulation model. Now, to overcome this problem, we can extend this kind of model over large area with the help of GIS and remote sensing. That is the beauty of geospatial technology. We can use partial power of this geospatial technology to extend this kind of location specific model to the large area. Now first we'll discuss how light efficiency model works. Particularly solar radiation which is received from the sun. About 41% of this solar radiation is a photosynthetically active radiation, PAR. Once PAR impinging on the crop, it is intercepted. Some part is transmitted to the ground, some part is reflected back, and some part is absorbed. This absorbed part is mainly utilized to drive the process of photosynthesis. So the CO2 that is converted for total gross photosynthesis is called GPP. The net photosynthesis, that is once we subtract release of the carbon dioxide through maintenance respiration, then it becomes the NPP. So here same this montage approach can be applied with the crop canopies and estimate the crop yield. So here light efficiency that depends on the phenological stages, nutrients, temperature stress, soil moisture stress. So all these biome, particular species, crop species, soil moisture or temperature and phenology can possibly derive from the remote sensing data. Similarly, FAPAR, fraction of absorbed photosynthetically active radiation, is also measured by the satellite remote sensing, particularly the optical remote sensing. You people must have heard about the MODIS. Now global products are available for the leaf area index, a fraction of absorbed photosynthetically active radiation from MODIS data. Similarly, NDVI also available from Indian satellite data like OCI. So these are product. Every 10 days you can get the image, whole India image, and use this for the crop modeling. Then PAR, photosynthetically active radiation, which we can derive from the solar radiation. And solar radiation can be estimated from the cloud properties or the directly from the half-hourly satellite image from the geostationary satellite data. So here we see one exercise what we have done. That is for the wheat yield. Here wide field sensor wheat data are used for the wheat crop classification. Then MODIS data on every 8-day basis, MODIS NDVI that is used to generate wheat crop NDVI after masking with the wheat crop mask. Then we have taken some ground observation at different locations in the Haryana and Western UP. For the FAPAR, we develop a relationship between FAPAR and NDVI. That relationship we develop for the reproductive phase and the vegetative phase. Then apply to estimate the FAPAR on a every 8-day basis. Then meteorological station, if you don't have satellite based solar radiation from the either insect 3D or you ghost data or some cloud properties, then you can use some weather observatory data like maximum minimum temperature. Here we have used and then applied to Bistow and Campbell model. Here we have got 10-15 stations within Haryana and surrounding, then interpolated every 8 days corresponding to the satellite image interval. Then interpolated PAR image is obtained. Light efficiency we have obtained from Haryana Agriculture University. With phenology, stage also obtained from the Haryana Agriculture University. Harvest index also. So these are the all constant on one time varying data. Then we can compute the yield. So another way we also you can use LA and FAPAR retrieval based on weighted difference vegetation index, which is derived from the near infrared and red reflectors. So WDI is equal to NIR reflectors minus C into red reflector. Here C is a nothing but soil line constant. Soil line constant, it is a NIR reflectors divided by red reflectors of the plowed soil. Means plowed or bare soil, if you retrieve reflectors of NIR and red and make ratio, that will give you the constant of this regression between NIR and red reflectors will give you a soil line constant. That using this soil WDI, we have applied that Monson-Sackey law. Most of the agrometeorologists, they have learned about this Monson-Sackey law. That is the amount of radiation that transmitted within the canopy to the ground depends on this exponential function. So this same we applied to estimate with the WDI alpha. Here is a nothing but extinction coefficient. WDI alpha, it is a asymptotic value of the WDI once saturation happen, light saturation take place. That is what called critical LA. Once FFR goes beyond 95%, then it is it correspond to the WDI alpha. So here you see this NDVI, remote sensing NDVI for Haryana. So Haryana mainly first week of December, you can see green patches are coming up, which is representing the wheat crop. Then as it goes up, then green by the last week of February or first week of March, like 5/3/2004, it becomes mostly green. So most of the crop, wheat crop, has reached to the maximum stage. Then after maturity, ripening is started, and it mature and harvested by the first week of April or second week of April. So it completely captures the growth dynamics of the wheat crops. So we can derive FFR by simple statistical relationship between the concurrent measurement of the FFR, LAI, along with the satellite data by locating by the GPS. So here we have done for some Western UP data, and you see here that one equation we have developed, that is SAVI against the LAI. So it is a LAI, SAVI as a function of LAI. So LAI, but here you are seeing that LAI leaf area index, which is saturating at the 3.3 or 2.5 to 3 LAI. So there is some problem is always there with the optical data. The saturation problem, NDVI or SAVI saturation problem is there. But if there is some sparse canopy, there's canopy is there like sugarcane and other crops, there is quite difficult to estimate LAI with the optical data. So here you see we have estimated for one vegetative period and another is a reproductive period, two equation. We have also tried another approach, FFR, scaling of FFR between NDVI and NDVI mean and NDVI maximum, absorption limit. Both we have used, and also we have tried to estimate for the CLAIRE model, that semi-empirical model based on WDI. Here you see WDI we are getting FFR alpha is 0.94, the saturation problem is there, and alpha, that extinction coefficient we have got for vegetative and reproductive stage 0.35 and the 0.5 for the extinction coefficient based on the WDI and relating against the LAI. So this is a CLAIRE model that we can use all this extinction coefficient and other things directly into the crop model for better estimate of the crop yield. So this same light efficiency model here, first we have estimated wheat area, then NDVI every 8-day NDVI from Modi's, then PAR, interpolated PAR for that 8-day period, then NDVI we have mass with the wheat crop area, that is FFR, NDVI related with the FFR, that relationship we applied to get the FFR for 8-day period. FFR can be applied with the multiplied with the PAR, then we can get the absorbed photosynthetically active radiation for every 8-day period. Then light usage efficiency, that maximum light usage efficiency downscale by the water stress and temperature stress scalar from the satellite remote sensing. Like here we have used LSWI, that is a land surface wetness index. We have used also water deficit index. We have used also vegetation temperature condition index for generating temporal every 8-day what is light usage, how light usage efficiency is varying over the wheat crop, downscaling light usage efficiency, then used to estimate NPP, or you can say dry matter every 8 days. So this dry matter, once you sum over the growing season of the wheat crop, you can get the total biomass multiply with the harvest index, you will get the final yield. So here you see we have estimated yield for Haryana and Western UP. So most of the district we are getting within 10% of the official estimate of the wheat yield in Haryana and Western UP, except first 3 districts where we are getting positive bias of 20 to 30% upward bias. This is because of temperature, because we have used estimate temperature as a estimator of the PAR, and we have not applied any adiabatic lapse rate, because this Haryana, that Panchkula and these 3 districts, they are little bit high elevation is there. So without taking into account the adiabatic lapse rate, if you interpolate, it goes wrong. So it is overestimating temperature and finally overestimating yield. Then we talk about simulation crop model. Crop simulation model are built program that simulate behavior of and processes of the plant as a function of weather, soil, and management. What input it require? They require weather on daily time base, rainfall, temperature, and the radiation. That's the majority. Soil parameter we require depth-wise moisture or depth-wise texture information. Crop parameter mainly phenology and morphological characteristic. Management mainly sowing dates, application dates of fertilizer, irrigation, and frequency also. Process, what it simulate: phenological development, transpiration, respiration, dry matter. Final output will get water balance component, evapotranspiration, biomass, LAI, yield. So there are so many models available. They are completely mechanistic model. There are radiation and water based model, and there are also simple only based on radiation. So here DSAT family which require phenotypic and genotypic coefficient, but there are certain model like EPIC, WAPOST, or wheat grows, which are completely radiation and water based model. They doesn't take into account the pest disease or any other kind of things. They are mainly radiation water based model. ORISA also, it is a radiation and water based model, and these are the model being highly used, extensively used for the large area, and they are being extended with the geospatial technology for the partially explicit derivation of the crop information and the yield estimation. So earlier in the Patel is a one program that forecasting agriculture output using space, agrometeorology, and land observation. That is carried out by the Ministry of Agriculture in collaboration with the ISRO. So this particular Patel project, point scale data are being used earlier to large scale wind forecasting for the central IGP area. Info crops are also used for the state level potato yield forecasting, but these all where district level weather is used and district level forecast yield models are developed, or it is parameterized and being used. So lack of timely availability of weather input, dependence on stochastic and weather generator for the forecast period is required. But if you want, we use partial approach like wheat grow, which is being used for the regional level wheat forecasting in Haryana. Was recently regional level crop assessment approach using WAPOST data simulation model. It is being used with the remote sensing data. But all this where weather information is generated through stochastic weather, means for prediction purpose, stochastic weather generator is used to estimate weather for the forecasting period. So, but this weather variable information is very coarse grit, derived from the meteorological observatory data only. So they may have little bit more error. If we try to make use of CLOP model, means climate model predicted weather or weather forecast for the remaining period in place of stochastic weather generator along with the crop model. Okay, actual weather, up to a period till we want to forecast we can make use of actual weather. Then we can use weather forecast data. So this can be a good example for the early warning. So geographical information system, as I said, it is one of the wonderful tool, and integrated use of this GIS and crop makes possible to extend or combine partial perspective of the GIS with the more stronger representation of temporal plant development process by the simulation model. What I want to say here, that means plant model, crop model simulate continuous and temporal plant development process. But for this we require high amount of data and large scale partially variable information, which is not possible. But GIS with the remote sensing, you can actually estimate the actual status of crop and get the partially explicit layer of information on weather, soil, moisture, LAI, initial sowing date, and then you integrate with the simulation model to get the partially explicit information on the crop yield. Similarly, climate model, which are mainly used to predict climate scenario and impact in many cases using downscaling approach. So this downscale weather with the regional climate model or WRF model can serve as a key input for the driving crop model. So this is a new area which is being developing called climate couple model. Now people are talking about climate couple modeling because agriculture affect the climate. At the same time, you can not forget that climate is affecting the agriculture and agriculture is also affecting the climate. So two-way process are governed. So for agriculture, how affecting the climate need to be understand, and that only understand through climate couple model. So climate coupling modeling or climate crop modeling now a newer technology being used to estimate large area crop production forecast or climate risk assessment. Crop model, they are based for the potential climate change impact assessment studies, water use, and helps in formulating adaptation strategy. So integration of these three tools, geospatial technology, crop model, and climate model, will pave a way for developing decision support system, early warning system, and climate risk assessment, or developing climate resilient agriculture. So here you can see, okay, I am demonstrating one approach where, okay, we have used WR, weather research forecasting model for weather forecast in atmospheric research weather. For which, okay, we have generated weather at the 7 week, 5 week in early advance, or 3 week, different week in advance, with the assimilation of the satellite remote sensing based land surface condition like leaf area index, land use land cover, or terrain condition. We have improved in the WRF model and improved the weather forecast. And this weather forecast assimilated into a DSET model, cirrus wheat and cirrus rice, for improving the crop yield prediction. We have used also Modi's LAI as a state variable for constraining, and also Modi's derived sowing date information for initial sowing date information into the crop model. So here you can see, okay, with the weather forecast, efficiency is improved by 25 to 30% improvement is there in the weather forecast compared to the default data. What I mean to say is, if you use default weather land surface condition in the WRF model, and you use, okay, some the land surface condition from the satellite data and use in the model, you can improve weather forecast by 25 to 30%. And we can see here RMSE has been reduced drastically with the simulation of land surface data. This data, how it can be incorporated into this, mainly for AWS weather observation, for current weather, and for forecast weather we can use climate model. Remote sensing, we can use NDVI or LAI as a state variable at discrete time step. Crop distribution, crop management, NBSS LUP, that is also soil map, which is derived from the satellite imagery only is also integrated with the crop model. So all partial information layer, for every grid of 1 kilometer or 10 kilometer, a crop model is run and output is written as a regional crop yield map. So here you see how this system works. Or it is a crop growth monitoring system where crop, cultivar, boundary, then weather observatory, management data, experimental data, all go along with the district code, and then finally every grid. Here you see Haryana, Punjab. We have categorized into a 1 kilometer grid, 10 kilometer grid. Sorry, not 10 kilometer grid. For every 10 kilometer grid, we have run the DSET serious wheat model and estimated the wheat crop yield. Initial sowing date, we have tried to get 3 dates, varying sowing dates for Punjab and Haryana, and inserted into the model. Then how we have planned for the early forecast. Okay, you see 7 days forecast, 15 days forecast, 30 days well in advance forecast, 40 days well in advance forecast. So first point scale, that is with the ISRO AWS station data till we are doing forecast. Means first 7 days weather forecast, WRF forecast. Means before last 7 days we have kept from the WRF forecast weather data. Before that, actual weather we have got from the ISRO AWS station data, 10-15 stations which are located in the Haryana, Punjab. Then second is 15 days weather forecast data from last maturity to early 15 days, and then ISRO weather data for actual weather observation. Similarly, that is for the point scale. Then there is a partial scale with a multiple lead time. We have used the NCEP graded database product of 10 kilometer resolution. We have downscale it 0.5 data graded to the downscale to the very high 0.25 degree to the very high resolution 10 kilometer grid scale. And along with that, WRF weather forecast data we have used for 10 kilometer grid scale, and finally used as a weather input. Here you see how it is improving. Agreement index also you can see, and also heat score and relative deviation. With 45 days advanced forecast with the weather forecast data, it is giving agreement index of 94%. But 7 days forecast or 15 days forecast, it is giving less than 90. That means if you have longer term duration of the weather represented partial weather for the long term duration, then we can have a better forecast, better agreement with the actual yield at the district level compared to the only if you have 7 days data. Because here not it is the how correct is the weather forecast information is vital. At the same time, we need to have a more accurate information about the representative weather of the on a partial domain. Because if you use only one district, one weather observatory, it is not representative of partial characteristic of that particular region. So it may not be correct. But if we use partially representative weather from the weather forecast, 10 kilometer data set, then it may be more accurate compared to the one district level weather observatory database for simulation of crop model. That is why this with more early forecast is giving higher accuracy, because we have got longer term duration of the weather being represented by the weather forecast. Similarly, same exercise we have also done for the drought risk assessment, simulation crop modeling for assessing drought stress and crop yield anomaly. Here you see 2009 and 2014. We have simulated for Punjab and Haryana with the DSET rice model. Now you see here, they are behaving nicely with the R square around more than 0.62, and in Haryana and Punjab it is 0.74. They are matching, or yield at district level is matching. But if you see beyond that yield anomaly, how this crop simulation model or climate crop model can be used to detect departure in the crop performance or to investigate crop loss or crop risk due to drought stress. So this kind of approach is very much useful for the crop specific drought monitoring, the crop specific risk monitoring. So here you can see majority of district you are seeing in 2009 Haryana, yield anomaly is a negative. Majority of district is giving more than 20% decline in yield, because 2009 was a highly drought, very high degree of drought stress was there across Western India and also in the Northern India. So majority of district, they are showing 20% less yield achieved compared to the long-term normal, and which is detected by the climate crop model based on simulated water stress also. Now here you see for vegetative growth stage and reproductive stage and maturity stage, there is a negative relationship between the water stress simulated by the climate crop model approach against the yield anomaly. Yield anomalies means the negative yield anomaly means crop loss from the less yield compared to the long-term normal. Positive yield anomaly means a higher yield compared to the long-term normal. But here you are seeing negative relationship with as water stress is increasing, crop loss is increasing. So all the states you are seeing, all the states there is a negative relationship, and we could able to detect yield losses due to water stress simulated by the climate crop model. Then as I said, I will show you also some example of the Maharashtra, particularly this Jalgaon, Bid, and this Pashan, and then Jalna. We have conducted one study to compare different kind of remote sensing driven crop model in Maharashtra region for the cotton crop. So we have tried machine learning based agrometeorological model, phenology based model based on the time series of satellite data from Modi's 16 days for 10 years. We have estimated phenology of the cotton crop, and they developed some phenological matrices and related with the crop yield and estimated crop yield. Then we have used also remote sensing driven light use efficiency model also with the inset based solar radiation, Modi's FPAR, LSWI water stress, ERA interim temperature data, and radiation use efficiency. We have also investigated DSET cropping system model for the cotton. So here we have done for last 15 years exercise for the Marathwada region with the rainfall, LST, NDVI, and SPI all computed for the 10 years on the monthly time scale for the machine learning based crop modeling. Then remote sensing with light use efficiency model we have tested. We have tested also simulation model for the cotton, CSM crop grow cotton model. This all is very much useful for the yield modeling. So here you can see Modi's time series. With the Modi's time series data, we could able to generate in start of season, peak NDVI, time of peak NDVI, maturity stage, and the length of growing season. So here you see amplitude, length of a growing season, and the peak value of NDVI derived from the time series analysis by applying time set procedure, phenological program. We have generated these matrices and related with the yield. You see positive correlation is obtained for the majority of phenological matrices like end of season, length of growing season, peak time, peak value, amplitude, all giving positive correlation with the crop yield. Then those matrices used with the multivariate analysis to develop regression model and applied to estimate the crop yield. So this is a phenological crop yield model which is giving more than 70% agreement with the district level cotton yield obtained in the Marathwada region. Then we have done also based on the all variable, monthly variable for the monthly variable from the June to the March next year. VCI, SPI, rainfall, LST, growing degree days for 20 years. Then use some machine learning technology like random forest regression. Random forest approach is applied to identify the most selected variable, critical variable based on the number of nodes and purity. So here, finally, based on this, we have could able to derive for September end. By September end, we could able to estimate model with more accuracy, 80%, December end, 78, February, 82%. So here we have tried, okay, with well in advance by September, by December, and by February, how much we can estimate cotton yield with respect to the with using random forest regression model. So this is okay, all about constructed model with the different kind of predictors find for the different time scale, means multiple lead time forecast of the cotton yield in the Maharashtra. Also, we have tried for the cropping system model. Here you can see also how we have done. We have used mainly the high resolution soil map, field data, crop management practices, and NASA power weather, like 10-kilometer gridded weather observation, and run with the genotypic and phenotypic coefficient derived from the Parbhani, and then we are using the CSM crop growth cotton model for the whole these five district at the block level. You see, we have this estimated for block level this cotton yield, but majority, okay, what we have seen, unless you do not make use of the remote sensing like LAI as a state variable or sowing date, you input sowing date which is actual sowing date from the remote sensing data. Then only you can constant get the better yield. Here you are seeing that relative deviation is okay, minus 42 plus 40 from the actual yield, because actual yield what we are getting here, that is all parameterization is very much important. How better parameterize variety specific parameterization, because here we have used only one variety specific genotypic coefficient, but if we get different block level, different variety specific crop coefficient, and also we can get the sowing date information along with the remote sensing. Then LAI, if we assimilate at the right stage, we can improve it correctly. Then okay, climate change. How this climate change is going to affect this agriculture, particularly global warming. But global warming, increased crop water requirement, increased frequency of drought, increased incidence of pest and disease. So particularly warming means rising of the temperature. Rising of temperature will affect particularly on growing season, whether there will be a faster growing period or longer growing season. Longer growing season will be there in the polar region where favorable temperature will be made available. But faster growing period will be there in the tropical belt where, okay, because of temperature and development rate has got curvilinear relationship, so development rate will be faster, so maturity will get enhanced, so finally duration will be lesser, shorter. Then it also affect the water requirement, because warming will give rise to the increasing in the atmospheric water vapor deficit, or you can say evaporative demand of the atmosphere will increase. Finally, crop water requirement will also increase. Increasing frequency of drought, because there will be an increase in the intensity of rainfall, but at the same time there may be a possibility of reduced number of rainy days. So more intensity of rainfall may cause flood, and reduced intensity of frequency of the rainy days may cause drought. So there will be a more frequency of drought and floods both. There will be an increasing humidity, and final rainfall leads to the increased incidence of pest and disease also. So these are the all regional level implication of the climate change on the agriculture in India. Then at the same time, with respect to climate change, there is a possibility observed or evidence are that climate atmospheric CO2 concentration is increasing. This increase in the CO2 concentration in the atmosphere may help agriculture to certain extent by increasing photosynthetic activity in certain crops like C3, C4 or what. Increase water use efficiency, pollution. It will increase pollution also. But here what we have to understand, this beneficial effect of the rising concentration of CO2 in the atmosphere will happen to certain extent. If global warming is very extreme, its negative effect cannot be compensated by the rising concentration of CO2 in the atmosphere. So final output will be negative or decline in the yield, because this beneficial effect will not compensate losses that will be caused by the global warming. So here, that is why we need to develop a kind of strategy which can harness more carbon, absorb more carbon and sequester into vegetation, so we can reduce CO2 in the atmosphere, and finally that can reduce the global warming, because CO2 is the main culprit gas that trap the heat and causes rise in the temperature. Other factor may be alteration in precipitation pattern, soil moisture conditions, surface runoff, increase occurrence of extreme weather condition, increase climate variability. These are the more pronounced effect what we will expect to observe in the Indian agriculture. So these are certain scenario what PCs, some IITM, Indian Institute of Tropical Meteorology, they have generated that increasing intensity by 1 to 4 mm per day. Number of rainy days also going to decrease by 15 days. Increased temperature may be 2 to 4 degrees during 2050s based on PC's model. So overall, if you see how agriculture is affecting how climate change is affecting the agriculture. So here, if you see, according to this particular, all crop in this region decline with the global yield with above 1% decrease. Most of the crop in this region are going to declining in yield, except rice, which will shows decline in yield at the 2 degrees centigrade. But in mountain region, highest steep rise in the temperature will be there, particularly in western Himalaya. We may experience 3 to 3.5 degree rise in the temperature. Okay, so here particularly globally, if you see more US, India or Africa, wheat, maize, in India wheat, significant decline in the yield is there. So this is what we are seeing in the particular in Northwest Himalaya, 3 to 5 degree by this end of this century, 3 times more warming than the plain, increased precipitation. This all will affect the yield, decline in yield of wheat crop, pest and disease, and shifting in the cultivating area, and also shifting in the apple belt. So I am showing you a particularly with mountain focus how climate change is going to affect, particularly in Himachal Pradesh. So here also we have used climate model, GCM output directly downscale with the regional climate model, and you inputted into the DSET model, rice, maize and wheat. And for the last 25 years, then we have assessed how it is impacting the crop yield. So here you see, all this is a simulation of the RACM climate model, temperature, rainfall, maximum, minimum temperature. They are particularly, if you see that these first two, that December, January, July, August, June, July, August, temperature is expected, maximum temperature particularly is expected to increase beyond 2010. It means that was simulated. Steep increase is there in the maximum temperature, and which is finally going to affect the crop yield. So here this all annual climatology and seasonal climate more variable we can generate from the regional climate model by downscaling technique. Then this model output of crop model DSET maize, cirrus maize simulation model. Here we have simulated for the almost 25 years current as well as up to 2025 future climate. So here you see, okay, there is a large scale variability in pattern about the yield. Yield is ranging from, okay, hardly you can say 500 kg to almost, okay, 3000 kg per hectare. Then we have seen here also, you see there is a variability in the maize yield, interannual variability, then also in the wheat yield. Erosion productivity. We have used also EPIC model. EPIC is a one process-based built model to describe soil management interaction at the towards hello. So here EPIC model, which is one of the best model which can be used for the soil erosion prediction, climate, soil management techniques, and so on. So here particularly when we use this model, it can be useful for the simulating crop yield, growth, nitrogen status, and so on. So there is a model which is called GEPIC, which is a geographically reference model, geographically interface model. So in geographically interface model, where we use the soil, land use, irrigation, weather as an input, we can simulate ET and yield and crop water productivity on a grid basis. So we have used certain climate change scenario, like world climate change scenario for 2020, 50s and 80s. Both usual and industrial scenario we have tried. We have collected soil sample, texture, and all soil related parameter. We have taken also management input, crop parameter input. We have tested calibrated model with the biomass and LAI in yield, all different parameter, and base parameter we have chosen for running the model on a 1 kilometer grid basis. You see here, okay, we have got yield validation for calibration with the 9 site. Then LAI in rice also calibrated with the model. Then this you can see, you are seeing map that is 1 kilometer grid map of the soil code, land use land cover code, and the gridded slope map. Along with the weather, we have used only one observatory, 1 kilometer world climate weather data to simulate the crop. Now here you see the statistic, what we are observing. So rainfall, we are seeing the rainfall, how it is changed in the 20s, 30s, 50s and 80s, both in the A2A scenario and B2A scenario. So we are seeing here mainly the mean temperature, which is going to be increased over the period of 3 timeline. Atmosphere CO2 also you are seeing here, that is also increased from baseline 1969, 1970, 361 to A2A 2432, and then A2A 50 is 590. That is a CO2 concentration is also going to increase. Rainfall, if you see rainfall, that is change in rainfall, percentage rainfall, that is going to be a positive mainly by 80s. You are seeing 70 to 85% increase will be there in the rainfall in A2A scenario, and 50 to 60% rise in rainfall in the B2A scenario in 80s. So this we have investigated its effect on the crop yield. So rice crop with A2A scenario without CO2 fertilization means if we assume that there is no CO2 increase, under that case you are seeing here mean yield 2080, when extreme warming will be there, 92% yield decline in yield will be there. But up to 2050s, 9%. Up to your current up to 2020 current year, there is no much decline in the yield of the rice without CO2 fertilization scenario. But if CO2 fertilization scenario, there will be not much decline in the yield, that you can see here. So even 2080 only, there will be some kind of one marginal decline we can see in the yield, particularly in the rice. But this is not the case with respect to the wheat crop. Let's see. This is okay for rice, how it is okay affecting the yield, particularly based on the reduction in the crop duration. With the more warming, rice crop is growing faster, less duration is available for photosynthesis, finally reducing crop yield. So here for wheat crop, you can see here decline in the yield by extreme warming in 2080s will be very high, around 40 to 40% decline in yield will be there. Throughout 2020, 50s and 80s, there will be a negative yield or decline in yield will be there without CO2 fertilization. Even with CO2 fertilization also, you are seeing there will be a decline in yield in 2020s and 2080s. Why 2020s? Because here there is a all effect on the winter rainfall. Where Dehradun Valley, their winter rainfall matters. So if rainfall is there, but by 2050s, there will be a not extreme warming is there that may not meet the water requirement. But 2050s, that is a still okay. There is a very high water stress is there, and rainfall is not very high. So it is causing some kind of decline in the yield. But 2050, because of positive effect of the increased rainfall, will compensate to certain extent. But extreme warming, that cannot be compensated even in case of wheat. So overall, you can see decline in the crop yield in 2080 means extreme warming scenario will be without CO2 fertilization will be there 40% in wheat, 20% in rice, and maize will be a 4%. Then there is also climate change impact on productivity. So wheat in climate change scenario, we have investigated for the Himachal Pradesh also. Here also you can see there will be a decline in the yield of the wheat crop, particularly in 2020s and 2080s. For 2050s, there will be no much decline in the yield across all block or district of the Himachal Pradesh. Then also some point scale studies, okay, so what it reveals about the report adaptation strategy, particularly with respect to wheat. Some KIDA, Central Research Institute of Dryland Agriculture, they have conducted for Akola, because I want to see here for Akola, and this decline in yield up to even you can say 10 to 20% is there across different timeline, 2020, 50 and 2075. That means wheat is highly sensitive to the climate change. But if we have okay some kind of adaptation strategy like okay irrigation supply, fertilizer management, or alteration of sowing date, that can change the scenario. So here you see 3 advanced sowing date to 200% rise in fertilizer and 1 extra irrigation can bring that negative dimension to the positive yield. So if you adopt adaptation strategy, whether all station, you can whether Akola, Ludhiana, whatever, if you have with the suitable adaptation strategy, we can bring yield, declining yield due to warming to the positive level. So adaptation strategy is very much critical to prevent or to curtail the risk due to the climate change. So that all about the climate change impact assessment and climate crop modeling. Little bit okay, I will tell you about the how geospatial modeling, agroclimatic drought, climatic and drought risk it can be useful. So we have done many studies with respect to monitoring agriculture drought. Here you can see that okay, particularly in Rajasthan, NDI anomaly index that capture very well the different kind of drought. So all yellow feature that gives you a drought affected areas vegetation, or blue that is means not drought affected month. So different indicators are there: vegetation condition index, vegetation drought index. We can predict drought also based on the remote sensing input like INSO NDI. Linkage we can develop based on INSO NDI or rainfall, which is a vital indicator for the early forecast of the drought. The NDI space time correlation for the crop yield departure and crop loss estimation. We can do certain kind of Markov random, this kind of data mining technique or a machine learning technique. Then some partial crop modeling like specific model, water requirement satisfaction index, all are useful for the crop modeling. So here you can see here that particularly in Rajasthan, by having this seasonal vegetation anomaly index, you can compute from the long-term data that can be used as an indicator of the crop loss or crop risk due to drought. So you can, if you have this indicator, then you are seeing that how food grain anomaly in the 2002, 2000, 2001 and 2002, how it is related with the food grain anomaly. So we can detect early crop loss in the food grain due to drought. Similarly, for Gujarat also, we have studied for long-term drought monitoring, and then you can see here 2000, 2001, 2003 and 2004 drought duration we could able to compute from the vegetation temperature condition index. Here it requires both land surface temperature and the NDVI data from MODIS. Then we have used this negative relationship between these two to extract vegetation temperature condition index. Then this vegetation temperature condition index is threshold or categorized into a different classes of stress and unstressed vegetation. Then every 8 days we can compute also drought duration, and here you can see here also on the right side, groundnut yield is highly related with the drought stress estimated from the VTCI. You see, with increasing in the period of drought stress or duration of the drought stress, there is a decline in the yield of groundnut in case of Gujarat. So this kind of departure in crop loss or crop risk due to the climatic and drought risk can also be assessed very accurately or partially with the geospatial technology. Same thing here you can see this on the left side, there is a 3-month SPI and Kharif season NDI anomaly correlation graph. So here you see all bluish and yellow area. That is a high correlation areas between 3-month SPI and the vegetation anomaly. So it shows that wherever high correlation is there between the NDVI and the rainfall, this SPI, that suggests that they are the highly drought prone areas, but they are highly vulnerable to the drought areas. Rest where correlation is poor, they are not highly vulnerable. So for La Nina and El Nino also we have assessed, and you see here SST anomaly, Nino 3 region, so South Oscillation Index is giving also good correlation with the NDVI anomaly, rainfall anomaly. So this all can be used as an indicator of the early assessment of the drought risk or climatic risk. Like we can use also soil water balance, crop specific soil water balance, along with the input of the satellite information like phenology, actually rainfall, all you can input into the water balance and compute the length of growing season, water requirement satisfaction index as a indicator of the food security and early warning. And you see here we have found good relation between the WRSC and the actual yield. They are because finally the water requirement satisfaction index is very much useful for depicting the actual crop growing condition for the decision making or contingency measures. Some for you people also, I wanted to show you some results with the Marathwada. We have done one drought vulnerability assessment by integrating MODIS related VCI, Chiefs rainfall related standardized precipitation index, SRTM DEM, socioeconomic data to derive sensitivity index, exposure index, and the adaptive capacity index. Integrated all these to derive agriculture drought vulnerability index. Here you can see we have derived agriculture drought vulnerability index for the Marathwada region, where Latur district were very highly vulnerable to drought, and blocks of Hanguli district were less vulnerable to the drought. So by integrating all those information partially available from the satellite data, even Chiefs rainfall data, and also other socioeconomic data can help you to determine vulnerability and risk related to the drought or climatic extreme weather event. There are various geospatial crop yield modeling programs and early warning system exist across India. India, we have Patel like that. Europe, Mars, monitoring agriculture with the remote sensing. Then FUSE, USA, famine early warning system. So these all working for developing, integrating satellite observation with the GIS and giving information for the for improving food security and farming system. Like Patel, how it works with the remote sensing, conventional space observation, agrometeorology observation, all we are inputting to derive different time of forecast. 4 forecasts we are giving of the different 10 major crops. Likewise, you said they are forecasting water requirement satisfaction index, what methodology I have shown, crop soil moisture water index, NDI anomalies, all are useful for depicting the crop monitor or crop early warning condition. Then Mars, they are using WAPOS crop model along with the satellite based input of the NDVI, climate data from geostationary satellite data, then soil and management input, simulate the crop yield, and along with the crop model, they are using also the meteorology based, trend based, and the simulation, this remote sensing based, the input for the final deriving crop yield, partially crop explicit crop yield information over whole European Union. Similarly, energy and water balance system is also being developed, which use our highly debated, or we have people know that Durant-Bros or Stewart equation, multiplicative Stewart formula. The crop growth is proportional to the actual evapotranspiration. So it uses mainly that Montet model and relative evapotranspiration model to forecast the crop yield. So here you see yield estimation in maize for South Africa, that is a fraction of how much yield is there. They are estimating based on the relative evapotranspiration estimated from the satellite observation, mainly thermal observation. So you can estimate ET and you can estimate a maximum evapotranspiration at different stages of crop growth and link it with the yield response factor as per the FAO methodology. So these are all about global scenario, and we have discussed in thoroughly about the geospatial crop modeling, how it can be useful for the climate change impact assessment and analyzing some climate related risks, particularly drought. If anybody has some question, you can welcome, or I am very much available to you to reply at my email address nrpatel@irs.gov. Thank you all.
Thank you very much, sir.
Yeah.
There are some questions. Participants.
Yeah.
First one from Dr. Umed Singh.
Okay,
Is
tell.
Patel available freely to the users or researchers?
What?
Is Patel is available freely to the users or researchers?
Yeah, Patel is a one program. Okay, Patel is a program, and Patel is implemented by at the different center, even Agromet AFMU. You understand? Agromet field unit, even in the Dapoli and Rahuri. That Dr. J.D. Jadhav, he is also nodal coordinator for that Patel program. So that these all agrometeorologists and agrometeorology field unit, they are attached with this Patel program, and they are receiving grant also. So Patel is not only the any kind of software, but it's a kind of program where technology is being developed across different AFME unit for the improving crop yield model, and that crop model are integrated with the crop area estimates by MNCFC, Mahalanobis National Crop Forecast Center at the New Delhi. So there are many organized IMD, Agriculture University, Mahalanobis National Crop Forecast Center, ISRO Center, all are working on this Patel program. So all researchers, whoever want to use, they can attach with any like ISRO Center. If you want to do some PhD something, you can join some PhD ISRO Center, or you can do PhD in collaboration with any ISRO Center. you will get access to the Fasal kind of technology and methodology. Okay, any more question?
Yes, sir. Next question is from Dr. Sumanta. How
Yeah.
reliable is MODI's data? For example, evapotranspiration, GPP, land cover maps.
Okay. More this data, okay, as on my experience is there because we already have flux tower data, which gives you a accurate measurement of the GPP and evapotranspiration. We are measuring this for the cropland and forest ecosystem. So Modi's GPP itself, because Modi's data, they are developed LAI and this data which are they have developed, that is based on the measure 4 biome types. They have not taken individual crop types or species. So they are in general underestimating almost 1/4 estimate of the actually what we observe. So what in my opinion is that Modi's data, if you are taking directly reflectors, 250 meter NDVI or reflectors, and develop your own equation, not directly depends on FFR of the Modi's or LAI of the Modi's. Instead of that, you develop your own equation, whether with the Sentinel data, LIS3, advanced sweeps, or Landsat. You develop your own equation for the field scale estimation of the LAI or FFR, and then you use in the model, or whether it is simulation model or the semi-empirical model. Then you can get the better crop in. Similarly for GPP also, FFR is required. So FFR you estimate with your regionally calibrated equation of FFR, and also you get the solar radiation, which is main driver of the photosynthesis. Unless you don't have the correct solar radiation data, you will not get the correct things. So whatever Modi has used, that is a half degree temperature data. So it is not accurate for the Modi's product, GPP product and ET products are not accurate. Nowadays, EcoStrace. Some products are available from EcoStrace or metric based products are available. They are more accurate compared to the Modi's. Any more question, please?
Yes, sir. Next question is from Dr. Anand Jadhav. Will
Yeah.
these climate smart models helpful to forecast sugarcane yield loss, either soil salinity or sodicity, particularly in western Maharashtra or canal command area?
Forecast crop yield or sodicity, what is talking? I do not understand.
Forecast sugarcane yield loss, either soil salinity or sodicity.
Okay, but particularly with respect to nutrient soil map, okay, if you have got okay soil salinity and sodicity, which for sugarcane, at least okay, I can tell okay that with the crop model, simulation model like aqua crop is a one model which has got okay good parameterization for the sugarcane crop over India. So parameters are developed, so it is working well for the sugarcane crop in India. But with respect to the salinity, all parameter, because finally what you need for this crop model, you have to first rigorously study sodicity or salinity and its impact on the crop yield and derive parameter which these crop models accept. If those parameters are not parameterized for the particular region or Marathwada region, then it may or may not work for the studying impact of the salinity or sodicity on the sugarcane crop yield through the climate smart model. Am I okay able to answer that? Okay.
Yeah.
Hello?
Yes. Hello, sir.
Yeah. More question, please.
Yes, sir. Next question is from Dr. Sumanta. Can machine learning models be used in place of simulation models? Which approach is more suitable?
Okay. Here I want to make it clear that machine learning, that is a training technique. Machine learning model require huge amount of training data set. If you have ground observation, like okay, if you are doing yield, if you yield estimation, so if you have okay large number of crop cutting experiment, along with the high resolution remote sensing data or UAV, for every crop cutting experiment, we have UAV measurement or drone related hyperspectral measurement, then we can establish better machine learning based technology. But if we don't have the ground measurement observation or training observation, then this kind of machine learning cannot replace the crop model. The crop model, okay, surely it gives only the potential yield, but if we calibrate those models for the specific region, then apply along with the remote sensing, derive some input, then it will definitely give better yield estimate compared to the machine learning, unless we don't have the training data set. Yeah,
Okay.
more question,
Thank
please.
you, sir. This is last question from Dr. Adrija Datta. How insect pest?
Yeah, please. How insect pest?
How insect pest can be monitored through the satellite images?
Yeah. Okay. Insect pest disease, nutrient stress. These are all are the water stress or heat stress, salinity stress. These are all the stress. So I can say as of now, optical remote sensing or multispectral remote sensing available can help you to detect the stress, means condition. But causes of stress is very difficult with the multispectral kind of remote sensing. If you have hyperspectral data, that can enables you to detect the pest and disease trace. So as on today, we don't have one good high resolution satellite data from hyperspectral sensor available for monitoring pest and disease. But if epidemics, a particular pest is in epidemic form like locust, last year in Gujarat or Banaskantha and different district where locust has impacted. So this kind of locust damage is very large and vast. So that can be easily monitored with the rainfall or land surface wetness index and NDI. Easily we can monitor with the locust damage on this. Like in Maharashtra, if pink bollworm or means spotted bollworm or cotton Heliothrix armagera, damage is very high. In case of cotton, it can be possible to detect even with the simple Sentinel or LIS3 kind of satellite data you can monitor. But if it is in vast, if it is small leaf level or small magnitude of damage is there, then we need to have some higher hyper spectral data which can detect different kind of stresses. Please, thank you. Any more question, please?
One question is, sir,
Yeah, please.
from Dr. Gopinath.
Yeah.
Can these models correlate with nutrient uptake model to predict the nutrient-driven yield assessment?
Nutrient uptake. Okay, EPIC. What I have shown here, one EPIC model that has got JPIC also. It is a geographically interface EPIC, erosion predict productivity impact calculator. It can simulate uptake CN and this uptake. Also it carbon and nitrogen loss, soil loss, and also it can estimate the soil erosion also. So there are many like DNDC. There are also other Rothmans. So many models are available which are having ability to estimate uptake also, CNN loss through whether crop uptake or through soil loss.
Okay.
Yeah, any more?
Thank you so much, sir.
Yeah, thank you very much.
Okay. On
Any
behalf
more question?
of organizing team, CAST, CSA, WM, MPK, KV Rahuri, and on behalf of all the participants of this 1 week online training program, I would like to express my sincere thanks to Dr. Patel, sir, for his very interesting and interactive lecture on geospatial crop modeling for climate risk and climate change impact assessment. Thank you so much, sir. With your permission, shall we close the session?
Yeah, please.
Thank you, sir. Thank you all.
Yeah.